Hi everyone, my name is Norah Tang and I'm a sophomore studying mathematics and computer science. My partner is Jessica Santers, who is a second year PhD at Duke EC department. Today I'm going to introduce you our project, Spectral Analysis for Constraint Codes, and our advisors are Professor Robert Kelderbank and Dr. Ahmed Hardy. So a little background for our project is that power spectrum analysis is very useful in the subject of bandwidth compression of write signals due to a certain coding scheme and signaling method. So our project and today's presentation are separated into the following two parts. The first one is the derivation of the power spectrum for general constraint codes with non-return to zero signaling, and the second part is its applications to two sets of constraint codes, TX and AX. But before we dive deeper into these two parts, I want to first clarify or define these underlying terms for you. So to begin with, what are constraint codes? So by the literal meaning, constraint codes have constraints on the encoded sequence. So for example, we can forbid certain binary patterns. By doing this, we can mitigate interference, prevent short pulses, and generate streams of bipolar directed current-free signals through balancing. And applications can be found in magnetic recording systems, flash systems, and optical recording devices. Non-return to zero signaling will convert the bit 0 to voltage level -A and bit 1 into voltage level +A. So following from that, we can define TX constraint code to be a symmetric code that forbids patterns in form of 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, and 1, 0, 0, 0, 1. And it will just forbid any patterns in this set from appearing in any of its code words. So let's take a look at this bit stream of 0, 1, 1, 0, 0, 0, 0, 1. And obviously it will satisfy the TX constraint, T1 constraint, and after NRZ signaling, 0 is converted to -A and 1 is converted to +A. So we will obtain this continuous write signal. And for AX constraint, it is just the asymmetric version of TX, and it will only forbid half of the forbidden patterns that appear in TX. So it will only forbid patterns of 1, 0, 1, and 1, 0, 0, 0, 1. This is just the same thing for TX. And the third idea is the power spectrum density. It describes the distribution of power into the signal's frequency components. So if we're given a bit sequence xn where each xn takes a binary value 0 or 1, its power spectral density is the Fourier transform of its autocorrelation function, which is the expected value of x0 times xj, where j here is the time lag. In this formula, d just denotes the complex exponential in form of e to the I2 pi ft. So our first part will be the derivation of the power spectrum for general constraint codes with NRZ signaling. Since Shannon showed in 1948 that finite state machine and directed graphs could represent constraints, we will just start from converting the coding scheme into a Markov chain. Let's take T1 constraint code, which forbid patterns of 1, 0, 1 and 1, 0, 1, 0 and 1, 0, 1 as example. It's not hard to see that after we have 0, 1, that is from state D, 0, A, 1, B to state B, or from state A by a 0 and state A and reach to state A and then to B followed by a 1. So starting from state B, we can only go to state C. So we will obtain a 0, 1, 1 instead of a 0, 1, 0, 0, which is never possible. So 0, 1, 0 is forbidden. The same thing will suffice for 1, 0, 1. And then we can define a run of length t to be a t1 minus 1 consecutive zeros following by a 1 at the end, and this run is to be defined of length t. So after some rearranging of the diagram, such as merging state, or we don't have splitting state, but yeah, basically merging state, we can obtain this run length diagram, and the number on top of each edge just denotes the length of all the possible runs. And then we're able to generate the one-step state transition matrix of this Markov process, and we will obtain this really important G. So for general x value, the matrix GD is in the following form, and all of our following derivations are centered around this GD. Recall how we reached to the continuous right signal. We start from a encoded sequence xn that takes binary values and forbids certain patterns. After NRZ signaling, we obtain a sequence an that satisfies an equals to xn minus 1. And lastly, we just simply extended the discrete an sequence into the continuous time domain. And this will give rise to our final continuous right signal. And we aim for the power spectrum of this WT. And based on the Markov chain, the run length diagram, and the one-step state transition matrix we just derived, we're able to come up with a formula that gives the power spectrum density of xn. And this involves the stationary distribution pi of the G1 matrix and the equilibrium probability P1, that is the probability of each individual bit to be 1. And based on the relationship that an equals to xn minus 1, we are able to derive the power spectrum for A2. And based on that, we can derive the continuous power spectrum density for WT. We can have a look here that D is in the form of e to the I2 pi fd. And let's move on to apply this method on TX and AX constraint codes. So these figures just show the power spectrum density for TX constraint codes when x is equal to 1, 2, 3, 4, 5, 6. And the blue lines represent the closed form solutions following the calculation we just derived, and the red lines are the Monte Carlo simulation. You can see that they just matches perfectly. Similarly, we can do the exact same thing for AX constraint codes by starting from its FSTD to its run length diagram and finally to the transition matrix. And recall that A1 constraint code forbids pattern of 101. And we can also obtain the spectrum for our AX constraint. The closed form solutions also match perfectly with the simulation. And notice that there is a sharp fall when the frequency is very close to 0. And this is the observation that is different for TX constraint. And lastly, I want to talk about a few notes here. First, we also successfully implemented the method for a code called lexicographically ordered constraint code, abbreviated as local, and its asymmetric A-local code. This is a new family of capacity achieving constraint codes that have much simpler encoding and decoding algorithm. But because we don't have enough time for the presentation, I just introduced the method on the simpler TX and AX code. And second, notice that non-return to 0 inverted signaling and NRZ signaling will give different results on sometimes the same coding scheme. However, for TX constraint code, the NRZ signaling, the result of the NRZ signaling is equivalent to a X infinity run length limited code with NRZI signaling. And our final takeaway is that this is a general method for all finite state machine-based constraint codes with NRZ signaling, and this is verified by Monte Carlo simulation. And this is also our conclusion. And here's our references. And thank you all for listening.